In the world of chemistry, things don't just happen. Molecules don't simply transform by magic. Every explosion, every medicine that heals, and every breath you take is the result of a meticulously choreographed dance of electrons. Today, we are pulling back the curtain to see the how behind the what. This is the world of reaction mechanisms. The foundation. First, let's look at the big picture. On the left, we have the net equation. It's the overall view, simply telling us that reactant A and B become product C. It's like knowing the starting point and the destination of a journey. But look closer at the mechanism. This is the detailed path. It breaks the journey down into steps. First, breaking old bonds, and then, forming new ones. Notice the energy shifts. Every movement has a cost and a consequence. Second, bond fission. At the heart of every change is bond fission, the breaking of connections. There are two ways this happens. First, homolytic cleavage. Think of this as a fair divorce. The electron pair is shared equally, resulting in free radicals, a highly reactive species with a single, unpaired electron. Then, there's heterolytic cleavage. This is unequal. One atom is more greedy and takes both electrons for itself. This creates ions, a positively charged cation and a negatively charged anion. This separation of charge sets the stage for what happens next. Electron seekers, finally, meet the key players that drive these reactions, the electron seekers. On one side, we have electrophiles, the electron lovers. These are electron-deficient species, often carrying a positive charge, searching for a negative source to stabilize themselves. Think of them as a magnet looking for its opposite. On the other side are nucleophiles, the nucleus lovers. These are the donors. They are electron-rich, often packed with lone pairs or negative charges, ready to supply the electrons that electrophiles crave. So, when you understand these three pillars, the path, the break, and the players, you aren't just memorizing equations anymore. You're reading the language of molecular change. Master the mechanism, and you master the chemistry. In organic chemistry, we don't just draw molecules, we map out their journey. To understand how reactions actually happen, we need to master the language of arrows. Think of it as the GPS for electron movement. The nucleophile and electrophile. Look at the main stage here. On the left, we have the nucleophile, in this case, a hydroxide ion. It's electron-rich, packed with high electron density. On the right is the electrophile, like this methyl bromide. It's electron-poor, and looking for a partner. Now, here is the golden rule you can never break. Electrons always flow from the source to the sink. That means the arrow must start at the nucleophile and point directly toward the electrophile. It's a one-way street from high density to low density. Double versus single heads, but notice the shape of the arrow. Not all arrows are created equal. A double-headed arrow indicates the movement of a full pair of electrons, the standard for most polar reactions. However, if you see a single-headed arrow, often called a fishhook, that's telling you only a single electron is moving. You'll usually see those in radical chemistry. Finally, let's avoid the mistake that trips up almost every student. Look at the warning box. In chemistry, our arrows show where the electrons go, not where the atoms go. Even though it feels like the atoms are moving, the arrow's job is to track the invisible flow of charge. Look at our high-energy timeline between the reactants and the final products. We hit a peak called the transition state, which drops us right into the world of intermediates. These are short-lived, high-energy molecules that dictate the entire pace of the game. First up, in blue, the carbocation. Think of this as an electron vacuum. It's sp2 hybridized with an empty p orbital, leaving it with only 6 valence electrons. Because it's electron deficient, it is a powerful electrophile, absolutely desperate for a nucleophile to swoop in and fill that gap. Now, the complete opposite, the carbanion in purple. This player is electron-rich, sporting sp3 hybridization in a full lone pair. With 8 valence electrons, it doesn't need help, it wants to attack. It's an aggressive nucleophile looking for any electron-poor spot to strike. Then we have the wildcard, the free radical. This one is sp2 hybridized with 7 valence electrons. That single, unpaired electron makes it incredibly twitchy and attack-ready. It doesn't want a pair, it's just seeking one more single electron to find its balance, making it the face of radical reactions. Here is the smarter note: to take home, intermediates are the high-energy bridge of a reaction. You can't bottle them up or isolate them, they move too fast. But, as you see in our stability scale at the bottom, their relative stability determines which reaction pathway the chemistry will choose to follow. So, understand the stability of the intermediate, and you can predict the product of the reaction. It's all about the middleman. Let's break down the energy landscape of a chemical transformation. The net change. Look at the first panel, the energy landscape. Every reaction has a starting line, the reactants, and a finish line, the products. The difference between them is the net energy change, or delta H in this view. If the products end up lower than the reactants, energy is released. It's the big picture of the reaction, but it doesn't tell us how hard the journey actually was. To understand the how, we look at activation energy. Think of it as a mountain climb. Even if the destination is downhill, you can't get there without first reaching the summit. This is the minimum energy required to initiate the reaction. The higher that mountain, the slower the reaction will be. You're looking at the barrier that keeps molecules from changing instantly. Now, let's look at the most critical moments of the journey. At the absolute peak of the mountain sits the transition state. This is the most unstable moment in chemistry. Bonds are in limbo, half broken and half formed. It lasts for a fraction of a second and can never be captured. It is pure instability. But, if your journey has a valley between two peaks, you've found an intermediate. Unlike the transition state, an intermediate is a real, though brief, chemical species. It sits in a valley of relative stability, a temporary rest stop before the final climb to the product. By mapping these peaks and valleys, we go beyond simple equations. We gain the power to predict how fast a reaction goes and exactly what happens at the most chaotic moments of molecular change. This is the heartbeat of reaction kinetics. Understanding mechanisms isn't about memorizing reactions, it's about understanding the logic of electrons. Once you know how they move, you can predict how almost any molecule in the universe will behave. If this helped you see chemistry in a new light, hit that subscribe button and leave a comment below on which mechanism you want to see broken down next. Happy learning!